In the late 19th century, the world of physics was firmly anchored in classical ideas that had been cultivated for centuries. These concepts, based on the works of great minds like Isaac Newton, James Clerk, Maxwell, and others, had shaped our understanding of the universe in ways that seemed absolute and unyielding. Classical physics provided a framework that explained the motion of objects, the behavior of light, and the forces that governed the physical world. By the 1800s, physics had already reached a level of sophistication where many phenomena could be explained with remarkable precision. Yet, despite its success, classical physics had certain limitations, and the dawn of the 20th century would soon expose those boundaries. At the heart of classical physics was Newtonian mechanics. Isaac Newton's laws of motion, published in his monumental work Philosophiae Naturalis Principia Mathematica in 1687, had revolutionized how we understood the motion of objects. Newton's laws described the relationship between a body and the forces acting on it, and how the body responded to those forces. These laws could explain the movements of planets across the sky, the trajectory of an apple falling from a tree, and even the complex motion of the tides. Newton's work built a framework that was both comprehensive and simple. It made sense of the world, offering equations that were predictive and universal. By the 19th century, classical physics had expanded beyond the work of Newton, incorporating the theories of thermodynamics and electromagnetism. In the realm of thermodynamics, scientists like James Joule and Rudolf Clausius were investigating the fundamental properties of heat and energy. They formulated the laws of thermodynamics, which describe the transfer of energy in the form of heat and the behavior of gases. The first law, for instance, stated that energy could not be created or destroyed, only converted from one form to another. This law had profound implications, setting the groundwork for understanding everything from engines to biological processes. Electromagnetism, another branch of classical physics, was grounded in the groundbreaking work of James Clerk Maxwell. Maxwell, in the mid-1800s, unified electricity and magnetism into a single theoretical framework known as the electromagnetic theory. His four equations, collectively known as Maxwell's equations, describe the behavior of electric and magnetic fields. They showed that light itself was a form of electromagnetic radiation, traveling through space as oscillating electric and magnetic fields. This understanding of light as an electromagnetic wave would serve as a cornerstone of classical physics for decades. Yet, despite its success, classical physics was not without its challenges. One of the most significant areas of struggle lay in understanding the nature of light. Classical physics, as described by Maxwell's theory, treated light as a continuous wave. However, this view of light failed to explain certain phenomena, such as the behavior of blackbody radiation. A blackbody is an idealized object that absorbs all incident radiation, regardless of frequency or angle. When such an object is heated, it emits radiation, and the intensity of this radiation depends on the temperature of the object. Classical physics predicted the behavior of this radiation through the Rayleigh-Jeans law, which worked well at lower frequencies. But at higher frequencies, the law predicted an infinite increase in radiation intensity, an absurd result known as the ultraviolet catastrophe. According to classical physics, this should have meant that objects at high temperatures would emit infinite amounts of radiation at very short wavelengths, but in reality, that was not the case. This paradox highlighted a deep flaw in the classical understanding of light and radiation. Alongside the blackbody radiation problem, another puzzling phenomenon existed in the study of heat. Classical physics struggled to explain why metals glowed at specific colors when heated, a problem known as the color of heated bodies. For example, as an object is heated, it first glows red, then orange, then yellow, and as the temperature increases, the color shifts towards blue and violet. Classical physics, which saw heat as a continuous form of energy, had difficulty providing an explanation for this specific, ordered sequence of colors. According to the laws of classical physics, heat should have been emitted uniformly, without the characteristic color shift seen in heated bodies. This discrepancy between theory and observation created a sense of unease among physicists. Additionally, classical physics could not fully explain the photoelectric effect, another key mystery of the late 19th century. In 1887, Heinrich Hertz discovered that ultraviolet light shining on a metal surface could cause the metal to emit electrons. However, classical theory could not explain why the intensity of the light did not affect the energy of the emitted electrons. Classical theory suggested that a more intense light should result in faster-moving electrons, but this was not observed. This inconsistency led to confusion and raised questions about the nature of light itself. Despite these growing issues, classical physics remained dominant, largely because the scientific community had not yet formulated a better alternative. The idea that light was a continuous wave, or that heat was an ever-flowing stream of energy, was so deeply ingrained in scientific thought that it was difficult to break free from. However, these unanswered questions created an atmosphere ripe for new ideas, and the groundwork for a revolutionary shift in scientific thinking was being quietly laid. At the turn of the 20th century, scientists were confronting a crossroads in their understanding of the natural world. Classical physics had served as the foundation for much of the technological and scientific progress of the previous centuries, but its limitations had become more apparent. The unresolvable issues surrounding blackbody radiation, the peculiar behavior of light and heat, and the inexplicable photoelectric effect all suggested that classical physics could no longer provide all the answers. It was at this juncture that new theories began to emerge, ideas that would challenge the very foundations of classical physics and usher in a new era of scientific discovery. One of the central figures in this transformation would be a man named Max Planck, whose work on blackbody radiation would soon lead to the discovery of quantum theory. Planck's radical new ideas would be the catalyst that sparked one of the most profound shifts in our understanding of the universe. The old laws of classical physics, which had once seemed absolute and comprehensive, were about to be shattered. But before delving into the revolutionary changes that Planck's ideas would bring, it is essential to understand the context in which they emerged. The classical framework of physics, although powerful and reliable for many phenomena, was being stretched to its limits. As the 20th century began, it became increasingly clear that something had to change. The scientific community was on the verge of a major breakthrough, one that would open the door to an entirely new realm of physics, a world governed by the strange and counterintuitive principles of quantum mechanics. The discoveries that followed would reshape everything from our understanding of the smallest particles to the nature of light itself. The very fabric of reality was about to be redefined. And it all began with a simple, yet profound, shift in how scientists thought about energy, a shift that would set the stage for the quantum revolution. As the 19th century drew to a close, the veil between classical and quantum physics was slowly lifting. The classical worldview, long seen as the ultimate explanation of the natural world, was being tested in ways that its creators had never imagined. With the unraveling of blackbody radiation and the mysteries of light and heat, the time was ripe for a new theory to emerge, one that would forever change our understanding of the universe and its underlying principles. By the dawn of the 20th century, classical physics was facing a crisis of confidence. Its explanations for many physical phenomena were no longer sufficient. One of the most pressing problems was the behavior of blackbody radiation. Classical theories, such as those developed by Rayleigh and Jeans, predicted an infinite amount of radiation at high frequencies. an absurdity known as the ultraviolet catastrophe. This paradox became a pivotal moment in the scientific community's recognition that classical physics was no longer enough to explain certain observations. In fact, this moment in history would soon give rise to something entirely new: quantum mechanics. Max Planck, a German theoretical physicist, found himself at the forefront of this intellectual upheaval. He had been studying blackbody radiation and was acutely aware of the failures of classical physics to describe this phenomenon accurately. In 1900, after grappling with this issue, Planck proposed a radical new hypothesis. Energy is not emitted or absorbed in a continuous manner, but rather in discrete packets, which he called quanta. This was a revolutionary shift in thought because it contradicted the prevailing view of energy as a continuous, flowing quantity. Planck's hypothesis arose from his mathematical attempt to solve the problem of blackbody radiation. He proposed that the energy emitted by a blackbody could only take on specific discrete values rather than any arbitrary value. The energy, according to Planck, was quantized, meaning it came in small chunks or packets. This was a profound departure from classical physics, which had assumed that energy could vary smoothly and continuously. To express this idea mathematically, Planck introduced the now famous equation equals E equals hniu, where sin E represents the energy of a quantum, 9h is a constant known as Planck's constant, and I/U is the frequency of the radiation. The introduction of Planck's constant, which is an incredibly small number, equals 6.626 times 10, 34 hours, equals 6.626 times 10, 34 joule seconds, was significant because it marked the first time that scientists recognized that certain physical properties could only exist in fixed, discrete quantities. Initially, Planck's idea was purely theoretical, designed to fit the observed data on blackbody radiation. It was not clear at the time that his concept of quantization would ultimately lead to the development of a whole new branch of physics, quantum mechanics. Planck himself was somewhat reluctant to embrace the full implications of his discovery. He believed that the quantization of energy was merely a mathematical tool to solve a particular problem, not a fundamental shift in our understanding of nature. However, the implications of Planck's work were far-reaching. In the years that followed, other scientists began to explore the consequences of Planck's ideas. One of the first to build upon Planck's work was Albert Einstein, whose 1905 paper on the photoelectric effect demonstrated that light itself was quantized, behaving like particles, later called photons. This marked the beginning of the idea that not only energy but light itself could be broken down into discrete quanta. Einstein's work on the photoelectric effect in 1905 was a crucial step in the acceptance of Planck's theory. In the photoelectric effect, when light of a sufficiently high frequency strikes a metal surface, it causes electrons to be emitted from that surface. Classical wave theory, which treated light as a continuous wave, failed to explain why only light above a certain frequency could cause electron emission, regardless of the light's intensity. Einstein proposed that light was made up of discrete packets of energy, photons, and that the energy of these photons was directly related to the frequency of the light. This was the first clear experimental evidence that energy was quantized. Einstein's idea of quantized light came from Planck's work, and his success in explaining the photoelectric effect cemented the growing acceptance of quantum theory. The implications of this were enormous. It suggested that the nature of light, matter, and energy was fundamentally different from what classical physics had proposed. What had been seen as continuous, smooth phenomena were revealed to be discrete, and energy was no longer thought to be infinitely divisible. The acceptance of Planck's quantum hypothesis was further solidified when Niels Bohr, a Danish physicist, developed a new model of the atom in 1913. Bohr applied Planck's ideas to the hydrogen atom and proposed that electrons in an atom could only occupy certain discrete energy levels, or orbits. Electrons could move between these orbits by absorbing or emitting specific amounts of energy corresponding to the differences in energy levels. This was a radical departure from the classical view of electrons as orbiting the nucleus in a continuous, smooth manner. The Bohr model was the first successful explanation of atomic structure and spectra based on quantization. Bohr's model of the atom led to a deeper understanding of atomic interactions and provided experimental predictions that could be tested. It also laid the groundwork for quantum mechanics, though the full development of the theory would take several more years. The Bohr model was an important milestone in the shift from classical physics to quantum theory, as it demonstrated the necessity of discrete energy levels for understanding atomic behavior. By the 1920s, the momentum for quantum theory was unstoppable. The work of scientists like Bohr, Einstein, and Planck had already transformed our understanding of energy and light, but the most dramatic shift came with the development of quantum mechanics as a full-fledged theory. This was largely the work of Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, who formulated the mathematical framework that underpins quantum mechanics today. Heisenberg's uncertainty principle, which he introduced in 1927, was one of the cornerstones of quantum mechanics. The uncertainty principle states that it is impossible to simultaneously know both the position and momentum of a particle with absolute precision. This was a direct challenge to classical physics, which assumed that it was possible to measure both of these properties precisely. In quantum mechanics, uncertainty was not just a result of experimental limitations, it was inherent in the nature of reality itself. Meanwhile, Schrödinger developed his famous wave equation, which described the behavior of quantum particles as waves. This represented another departure from the classical worldview, which viewed particles as individual, well-defined entities. Schrödinger's equation allowed for a more fluid, probabilistic interpretation of particle behavior, one in which particles could exist in a range of states until measured. The development of quantum mechanics was further complemented by the work of Dirac, who unified quantum mechanics with special relativity, leading to the prediction of antimatter and the development of quantum field theory. The theory of quantum mechanics was now an established framework for understanding the behavior of particles at the microscopic scale. Together, these scientists built a new and radically different understanding of the physical world. They had taken the ideas of Planck's discrete energy quanta and transformed them into a comprehensive theory that could explain everything from the behavior of electrons in atoms to the nature of light itself. Quantum mechanics not only revolutionized physics, but it also led to groundbreaking technologies such as semiconductors, lasers, and quantum computers, which have transformed industries ranging from electronics to medicine. The acceptance of quantum mechanics marked the end of the era of classical physics. The deterministic laws of Newton, Maxwell, and others were replaced by probabilistic laws that governed the microscopic world. In this new framework, the universe was no longer a deterministic machine, but a complex, uncertain web of probabilities and possibilities. The quantum revolution had broken down the barriers of classical physics and opened up new ways of understanding reality. The legacy of Max Planck's quantum discovery cannot be overstated. It not only solved the blackbody radiation problem, but also set in motion a scientific revolution that would redefine our understanding of the universe. Planck's work marked the birth of quantum theory, which continues to shape the future of physics, offering answers to questions we have yet to fully explore. From the smallest particles to the vastness of space, quantum mechanics has become the foundation of modern physics, and it all started with the moment when Max Planck proposed that energy, instead of being continuous, was quantized. This moment in history represents the breaking point for classical physics. It was a breakthrough that shattered the old ideas and forged a path toward a new scientific understanding. What followed was a century of discoveries, leading us into an era where the strange and counterintuitive nature of quantum mechanics is the key to unlocking the mysteries of the universe. And at the heart of it all was that one pivotal discovery: energy is quantized. From this fundamental realization, everything else began to fall into place, changing the course of science forever. The study of blackbody radiation is one of the most significant and puzzling problems in the history of physics. For centuries, scientists had been exploring the nature of heat and light, trying to understand how objects radiated energy when heated. In the 19th century, the concept of a blackbody, an idealized object that absorbs all incident radiation and emits radiation at a characteristic spectrum, became central to these investigations. But despite the advancements in classical physics, the problem of blackbody radiation remained unsolved. Classical theories predicted results that were clearly at odds with experiment, and this discrepancy became one of the most pressing issues in the scientific community. A blackbody is a theoretical object that absorbs all radiation falling upon it, without reflecting or transmitting any light. Such an object is said to be in perfect thermal equilibrium, and its emission of radiation depends solely on its temperature. The radiation emitted by a blackbody is what is called blackbody radiation, and it has some very unique characteristics that set it apart from other types of radiation. The most important of these characteristics is the spectrum of the radiation emitted. A blackbody emits radiation across a broad range of wavelengths, with the intensity of radiation depending on the temperature of the body. In the 19th century, scientists were very familiar with the concept of blackbody radiation, but they did not fully understand how it worked. The work of earlier physicists had laid the foundation for investigating this phenomenon. For example, Sir Isaac Newton had already discussed the properties of heat and light in his work, but the theory was still in its infancy. While the laws of thermodynamics and electromagnetic theory had been established, they were not enough to explain the specifics of blackbody radiation. The classical understanding of light was based on the wave theory, which suggested that light was a continuous wave that spread through space. According to this theory, light waves could have any frequency or wavelength. As a result, classical physics predicted that an object at any temperature would emit radiation across all wavelengths in a continuous manner. This idea seemed straightforward and intuitive. However, experiments revealed something very different. In the late 19th century, scientists began performing detailed experiments on the radiation emitted by hot objects. These experiments showed that the radiation emitted by a blackbody did not match the predictions of classical physics. The most notable experimental result was that the intensity of radiation did not increase indefinitely at high frequencies as classical theory suggested. Instead, it followed a specific pattern. As the temperature of a blackbody increased, the intensity of radiation increased, but the peak of the radiation spectrum shifted toward shorter wavelengths. The experimental data also showed that blackbodies emitted more radiation at higher temperatures, but the key issue was that classical physics, which treated energy as a continuous flow, predicted that an object should emit infinite amounts of radiation at short wavelengths, particularly in the ultraviolet part of the spectrum. This prediction, known as the ultraviolet catastrophe, was clearly at odds with experimental observations. In reality, the intensity of radiation at shorter wavelengths did not increase indefinitely. It reached a peak at a certain wavelength and then began to fall off. This discrepancy between theory and experiment represented a significant challenge for classical physics. The ultraviolet catastrophe was the result of applying the Rayleigh-Jeans law, which was derived from classical physics, to the problem of blackbody radiation. The Rayleigh-Jeans law was based on the idea that the energy of radiation was continuously distributed across all wavelengths, and it predicted that the energy would increase without bound as the wavelength decreased. In other words, it suggested that a black body would emit infinite amounts of radiation at very short wavelengths, leading to the absurd conclusion of infinite energy. This result was completely unphysical. The universe, as we observe it, does not contain infinite amounts of radiation, nor does the energy emitted by heated objects increase without bound. The discrepancy between classical predictions and experimental observations was profound, and it cast doubt on the adequacy of the classical understanding of energy and radiation. The problem of black-body radiation became a central issue in the scientific community during the late 19th century. Theories had been developed that predicted the behavior of radiation from a black body, but these theories could not explain the observed data. Classical physics had reached a dead end, and scientists were struggling to find a solution. The search for a new theory to explain black-body radiation was one of the key motivations for the development of quantum mechanics. At this stage, a breakthrough was needed. The key to solving the problem lay in understanding the true nature of radiation and energy. It was clear that the classical view of continuous energy was incomplete, and that something more fundamental was missing from the equation. What physicists needed was a new way of thinking about energy, a way that could explain the observed results and resolve the ultraviolet catastrophe. In the face of this challenge, Max Planck, a German theoretical physicist, began working on a new theory to explain black-body radiation. Planck was already an accomplished scientist, and he had a deep understanding of the existing theories of thermodynamics and electromagnetism. But he realized that the classical approach was insufficient to explain the behavior of black-body radiation. He knew that a radical shift in thinking was needed. Planck's approach to solving the black-body radiation problem was based on a combination of mathematical analysis and empirical data. He began by considering the classical theories and their shortcomings, then introduced a new idea: energy could not be emitted or absorbed continuously, but rather in discrete packets, or quanta. This was the key insight that would ultimately resolve the issue of black-body radiation. At first, Planck's hypothesis was purely mathematical. He introduced the concept of quantized energy in order to fit the experimental data. His goal was not to propose a new fundamental theory of the universe, but simply to solve the problem at hand. However, the consequences of Planck's idea would go far beyond the specific issue of black-body radiation. Planck's mathematical model for black-body radiation involved assuming that the energy of a system could only take on specific, discrete values. He proposed that energy levels in the system were quantized, and that the energy of a system could be described by the product of a constant, now known as Planck's constant, and the frequency of the radiation. Planck's equals E equals h/u, where E is the energy of a quantum, h is Planck's constant, and NIU is the frequency of the radiation, was born from this hypothesis. This equation would become one of the most important results in the history of physics. Planck's quantization idea allowed him to derive a formula for the intensity of radiation emitted by a blackbody, known as Planck's law. Planck's law correctly described the observed data for blackbody radiation, resolving the ultraviolet catastrophe that had plagued classical physics. This was a monumental breakthrough, as it provided the first consistent explanation for blackbody radiation. Planck's law accurately predicted the intensity of radiation at different wavelengths, and it explained why the radiation intensity did not increase indefinitely at short wavelengths, as classical physics had predicted. Despite his success, Planck did not initially embrace the full implications of his discovery. He saw his hypothesis of quantized energy as a mathematical tool to solve a specific problem, not a fundamental shift in our understanding of the universe. Planck himself was hesitant to accept the idea that energy itself might be inherently quantized, and he continued to view his work as a temporary solution rather than a permanent theory. However, the importance of his discovery became clear in the years that followed, as other scientists, including Albert Einstein, Niels Bohr, and others, would build upon his work and expand it into the framework of quantum mechanics. Max Planck's discovery that energy is quantized, and his formulation of Planck's law represented a turning point in the history of physics. The problem of black-body radiation, which had eluded classical physics for years, was finally solved, but this was only the beginning of a much larger revolution in scientific thought. Planck's equation not only resolved the ultraviolet catastrophe, but also opened the door to a B5R, radically new way of thinking about energy, light, and the nature of the universe itself. At the time, Planck's hypothesis was still considered a mathematical trick to solve a specific problem, and he himself was reluctant to accept its full implications. However, the impact of his work would resonate far beyond black-body radiation. Planck's idea that energy could only exist in discrete packets, what he referred to as quanta, was a profound shift from the classical view, which held that energy could be divided into any arbitrary amount. Planck's hypothesis introduced the concept of quantization into physics, a concept that would become the cornerstone of quantum theory. One of the immediate consequences of Planck's work was the realization that energy was not a continuous, flowing substance as classical physics had assumed, but was instead fragmented into tiny, indivisible chunks. This understanding of energy as discrete packets fundamentally changed how scientists viewed the interaction between matter and radiation. Planck's work challenged the very foundations of classical physics, where energy had been thought of as a smooth, continuous entity that could be divided and distributed as needed. Planck's quantization of energy laid the groundwork for an entirely new framework of physics that would later be expanded upon by scientists like Albert Einstein, Niels Bohr, and Werner Heisenberg. Though Planck himself was cautious about embracing the full implications of his discovery, the broader scientific community quickly recognized the significance of his work. In 1905, Albert Einstein would use Planck's idea of quantized energy to explain the photoelectric effect, providing further evidence for the quantization of energy and cementing the foundations of quantum mechanics. Einstein's work on the photoelectric effect demonstrated that light itself could be thought of as a stream of discrete particles, or photons, rather than a continuous wave. This was another radical departure from classical physics, which treated light as a continuous electromagnetic wave. Einstein's insight was crucial, as it confirmed that the idea of quantized energy had real-world applications and could explain phenomena that classical physics could not. Einstein's work on the photoelectric effect built directly upon Planck's work on black-body radiation, but it also extended the idea of quantization to light itself. Einstein's explanation of the photoelectric effect was one of the first instances where the quantization of energy was applied to the nature of light, providing experimental evidence for the particle-like behavior of electromagnetic radiation. This was a major milestone in the development of quantum theory, and it set the stage for further advances in the early 20th century. Einstein's work, alongside Planck's, showed that energy, whether it was associated with light or with matter, could no longer be thought of as a continuous, flowing substance. It was, instead, discrete and quantized. Planck's work was also pivotal in the development of the Bohr model of the atom. In 1913, Niels Bohr used Planck's quantization of energy to explain the discrete energy levels of electrons in atoms. Bohr proposed that electrons orbit the nucleus of an atom in specific, quantized orbits, and that the energy associated with each orbit was also quantized. When electrons moved between these energy levels, they absorbed or emitted energy in the form of discrete packets, or quanta, corresponding to the difference in energy between the levels. This was a groundbreaking idea, as it provided a clear explanation for the observed spectral lines of hydrogen and other elements, which had been a long-standing mystery. Bohr's model was a direct application of Planck's idea of quantization, and it marked the beginning of the quantum revolution in atomic theory. The success of Bohr's model led to further developments in quantum mechanics. In the 1920s, scientists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac would develop a complete quantum mechanical framework that explained the behavior of particles at the microscopic scale. Heisenberg's uncertainty principle, introduced in 1927, was a key result of quantum mechanics. The uncertainty principle stated that it was impossible to know both the position and momentum of a particle with absolute precision. This was a direct challenge to classical physics, which assumed that both position and momentum could be measured exactly. The uncertainty principle was one of the key insights of quantum mechanics, and it highlighted the fundamentally probabilistic nature of the quantum world. Meanwhile, Schrödinger's wave equation, developed in 1926, provided a mathematical description of the behavior of quantum particles. Schrödinger treated particles, such as electrons, as waves rather than as individual points in space. This wave-like behavior was in stark contrast to the classical view, which saw particles as discrete, localized entities. Schrödinger's equation allowed physicists to calculate the probability of finding a particle in a given location, and it laid the foundation for the development of quantum field theory. The development of quantum mechanics, spurred by Planck's work, represented a fundamental shift in our understanding of the physical world. Where classical physics had been deterministic and continuous, quantum mechanics was probabilistic and discrete. Classical physics had been based on the idea that the universe operated like a machine, with clear, predictable laws governing the motion of objects. Quantum mechanics, however, revealed a universe that was far more complex, where particles behaved in ways that were difficult to predict, and where uncertainty and probability were intrinsic to the fabric of reality. The implications of Planck's discovery went far beyond the theoretical realm. The new quantum framework that emerged in the 20th century had profound technological consequences. Quantum mechanics is the foundation of modern technologies, such as semiconductors, lasers, and quantum computers. The invention of the transistor, which forms the basis of modern electronics, was made possible by the principles of quantum mechanics. Lasers, which have applications in everything from telecommunications to medicine, rely on quantum processes such as stimulated emission and energy quantization, and the development of quantum computers, still in its early stages, promises to revolutionize fields such as cryptography, artificial intelligence, and drug discovery. Quantum mechanics also has profound philosophical implications. The probabilistic nature of quantum theory challenges our intuitions about the nature of reality. In the quantum world, particles do not have definite positions or velocities until they are measured, and their behavior is governed by probability, rather than certainty. This has led to philosophical debates about the nature of reality, the role of the observer, and the limits of human knowledge. Some interpretations of quantum mechanics, such as the many worlds hypothesis, suggest that the universe may branch into multiple realities depending on the outcomes of quantum measurements. These ideas challenge our classical notions of determinism and causality, and have led to new ways of thinking about the universe. The acceptance of quantum mechanics marked the end of an era in physics. Classical physics, with its elegant and deterministic laws, had been the foundation of scientific understanding for centuries. But with the advent of quantum theory, a new worldview emerged, one in which uncertainty, probability, and quantization were the fundamental principles governing the behavior of matter and energy. Planck's work in solving the problem of black-body radiation played a central role in this paradigm shift. Max Planck's discovery of the quantization of energy in 1900 may have started as a mathematical solution to a specific problem, but it ultimately marked the beginning of a scientific revolution. Planck's equation, E equals hniu, not only resolved the problem of black-body radiation, but also laid the foundation for the development of quantum mechanics. The work of Planck, Einstein, Bohr, Heisenberg, Schrödinger, and others transformed our understanding of the physical world and led to the development of technologies that have reshaped our daily lives. From the smallest particles to the vastness of space, quantum mechanics has become the foundation of modern physics, and it all began with the moment when energy was revealed to be quantized. At the end of the 19th century, scientists had reached a peak in their understanding of classical physics. Yet, one of the most intriguing and unresolved issues remained the behavior of light and heat. The prevailing theories at the time, grounded in classical mechanics and thermodynamics, could not explain all the phenomena observed in the physical world. Among the most pressing problems was the issue of black-body radiation, which had puzzled physicists for years. The equations derived from classical theories could not explain why black bodies, theoretical objects that absorb and emit all radiation, did not follow the predicted patterns, especially at higher frequencies. The discrepancy between theory and observation became known as the ultraviolet catastrophe. It was this problem that led a brilliant mind, Max Planck, to introduce a revolutionary idea that would change the course of physics forever. Planck's contribution to science cannot be understated. At the time, the concept of energy was thought of as something continuous, like a smooth, unbroken stream. Classical theories assumed that energy could take on any value anywhere along this stream. But this understanding was challenged when Planck, working on the problem of black-body radiation, proposed an entirely new way of looking at energy. Planck's hypothesis was simple, yet radical. Energy was not continuous, but rather quantized. That is, energy could only exist in discrete amounts, or packets, rather than as a smooth flow. This idea of quantized energy was a direct departure from the classical understanding, and it provided the answer to the mystery of black-body radiation. At the heart of Planck's work was his attempt to reconcile the observed behavior of black-body radiation with the theoretical predictions of classical physics. Black-body radiation is the emission of electromagnetic radiation from an idealized object that absorbs all incident radiation and emits radiation according to its temperature. The problem arose when classical theories, based on the continuous nature of energy, predicted that the intensity of radiation would increase without bound as the frequency of the radiation increased. This was clearly not the case in experiments, where the intensity of radiation increased only to a certain point before decreasing at higher frequencies. Planck approached the problem by considering the nature of energy in the system of oscillating atoms within the blackbody. Classical physics had assumed that these oscillations could have any frequency, meaning that energy could be emitted or absorbed at any level. However, this assumption led to the ultraviolet catastrophe, where the amount of radiation emitted at high frequencies would go to infinity. To solve this problem, Planck made a bold assumption. He proposed that the oscillating atoms could only absorb or emit energy in discrete amounts, or quanta, which were proportional to the frequency of the radiation. Planck introduced a new constant, now known as Planck's constant, h, and suggested that the energy of each quantum was proportional to the frequency of the radiation. This relationship was given by the equation E equals hniu, where E is the energy of the quantum, h is Planck's constant, and nu is the frequency of the radiation. This equation provided a way to quantify energy in discrete amounts, and it marked the first step toward a new understanding of energy and radiation. Planck's hypothesis was groundbreaking because it suggested that energy was not continuous, as had been assumed, but was instead made up of discrete packets. This idea was completely at odds with the classical view, which had always assumed that energy could vary smoothly and continuously. Planck's introduction of the idea of energy quanta was the seed that would eventually grow into the theory of quantum mechanics. At first, Planck himself was unsure of the implications of his work. He was primarily concerned with solving the problem of black-body radiation, and he did not fully grasp the far-reaching consequences of his hypothesis. In fact, he initially viewed the quantization of energy as a mathematical convenience, a trick to make equations fit the experimental data. He did not see it as a fundamental change in the nature of energy itself. However, as Planck continued to refine his work, it became clear that his hypothesis was not just a mathematical tool, but a fundamental insight into the nature of the universe. The implications of quantized energy were far-reaching, and they would eventually lead to the development of quantum mechanics. Planck's idea that energy comes in discrete packets would lay the groundwork for the next generation of physicists to build upon, including Albert Einstein, Niels Bohr, and Werner Heisenberg. In the years following Planck's initial work, other scientists began to take his ideas further. Einstein, for example, used Planck's quantization concept to explain the photoelectric effect in 1905. Einstein demonstrated that light, too, could be thought of as being quantized, existing in discrete packets called photons. This was a direct application of Planck's idea of quantized energy, but it extended it to light itself, showing that the quantization of energy was not limited to black-body radiation, but applied to all forms of electromagnetic radiation. Niels Bohr also built upon Planck's work in his model of the atom. In 1913, Bohr proposed that electrons in an atom could only occupy specific energy levels, and that when an electron moved between these levels, it would emit or absorb energy in discrete amounts. This was a direct extension of Planck's idea that energy is quantized, and it explained the observed spectral lines of hydrogen. The concept of quantized energy was further developed by the work of Werner Heisenberg, who formulated the uncertainty principle, and Erwin Schrödinger, who developed wave mechanics. Together, their work formed the basis of quantum mechanics, a new and revolutionary theory that described the behavior of particles on the atomic and subatomic scale. The shift from classical physics to quantum mechanics was not instantaneous, and it involved significant conceptual challenges. The idea that energy could only take discrete values was difficult to accept for many physicists, as it directly contradicted the smooth, continuous nature of energy that had been so deeply ingrained in the classical worldview. However, the experimental successes of quantum theory, including Einstein's explanation of the photoelectric effect and Bohr's model of the atom, helped to establish the validity of Planck's hypothesis. Planck's hypothesis laid the foundation for quantum mechanics by introducing the idea that energy was not continuous, but discrete. His work helped to resolve the problem of black-body radiation and opened the door to a new way of thinking about energy, light, and matter. While Planck himself did not fully realize the magnitude of his discovery at the time, his introduction of the concept of quantized energy was the spark that ignited the quantum revolution. By the early 20th century, Planck's hypothesis had already begun to shape the future of physics. The quantization of energy would become a cornerstone of quantum theory, and it would lead to an entirely new understanding of the microscopic world. The implications of Planck's work would extend far beyond the specific problem of black-body radiation, and his ideas would form the basis for the scientific advancements of the next several decades. At the heart of Planck's hypothesis was the realization that the universe is not continuous, but is instead made up of discrete units of energy. This fundamental shift in thinking would change the way we understand the behavior of light, matter, and energy, and it would set the stage for a new era in physics. The quantum revolution, which began with Planck's hypothesis, would redefine the laws of nature and lead to technologies that have transformed our world. The impact of Max Planck's hypothesis that energy is quantized was profound, not just for blackbody radiation, but for the entire fabric of physics itself. Planck's revolutionary idea that energy could only exist in discrete amounts, or quanta, did not merely solve the blackbody radiation problem, it planted the seed for an entirely new way of understanding the physical world. At the time, Planck himself could not have fully grasped the far-reaching consequences of his discovery, but as subsequent developments in physics unfolded, it became clear that Planck's hypothesis would form the cornerstone of the emerging quantum theory. In the years following Planck's formulation of the quantum hypothesis, the scientific community began to realize that his idea of quantized energy extended far beyond the specific problem of blackbody radiation. As quantum theory began to take shape, Planck's concept of energy quanta would become integral to explaining a host of previously unexplainable phenomena. The first major breakthrough after Planck's work came in 1905, when Albert Einstein extended Planck's idea to light itself. Einstein's explanation of the photoelectric effect was one of the key moments in the history of quantum theory. In this effect, when light of a certain frequency strikes a metal surface, it causes the emission of electrons. Classical wave theory of light, which treated light as a continuous electromagnetic wave, could not explain why only light above a certain frequency would cause electron emission, regardless of the intensity of the light. Einstein, building on Planck's concept of energy quanta, proposed that light was composed of discrete packets of energy, or photons. The energy of each photon, Einstein suggested, was proportional to the frequency of the light, equals E equals hn nu. The same relationship Planck had introduced for blackbody radiation. Einstein's explanation of the photoelectric effect provided experimental confirmation of the quantization of light, further solidifying the foundations of quantum theory. In this way, Planck's idea of quantized energy extended from the realm of thermal radiation to the very nature of light itself. Einstein's work on the photoelectric effect showed that energy could be quantized in the form of particles, photons, and that this quantization was not limited to heat or electromagnetic radiation, but was a fundamental characteristic of all forms of energy. This realization led to a paradigm shift in how scientists thought about the nature of light and matter. Classical physics had treated light as a continuous wave, and matter as a collection of particles governed by Newton's laws. But the quantum theory that was emerging would show that both light and matter had properties of both particles and waves, a duality that would prove to be one of the cornerstones of quantum mechanics. The wave-particle duality, which describes how entities like light and electrons can exhibit both particle-like and wave-like behaviors, became a central theme in quantum theory. The development of quantum mechanics continued to build on Planck's original hypothesis, and in 1913, Niels Bohr applied Planck's concept of quantized energy to the structure of the atom. Bohr's model of the atom, which was inspired by Planck's ideas, proposed that electrons in an atom could only occupy specific energy levels, or orbits, around the nucleus. When an electron moved between these energy levels, it would absorb or emit a discrete amount of energy, precisely the kind of behavior predicted by Planck's hypothesis. Bohr's model explained the observed spectral lines of hydrogen, which had puzzled scientists for years. The discrete energy levels of electrons in the atom corresponded to the specific wavelengths of light emitted when electrons jumped between these levels. Bohr's work, which was built upon Planck's quantization idea, became a cornerstone of atomic physics and marked the birth of quantum theory in its current form. The success of Bohr's model was soon followed by even more revolutionary ideas. In the mid-1920s, the development of wave mechanics by Erwin Schrödinger and the uncertainty principle by Werner Heisenberg would take the quantum theory to its next stage. Schrödinger's wave equation, which described the behavior of quantum particles as waves, provided a powerful mathematical framework for understanding the microscopic world. Schrödinger's equation showed that, instead of following definite paths like classical particles, quantum particles behaved like waves, existing in a superposition of possible states until measured. Heisenberg's uncertainty principle, formulated in 1927, was another key concept that arose from the quantum revolution. The uncertainty principle stated that it is impossible to simultaneously know both the position and momentum of a particle with absolute precision. This was a direct challenge to classical physics, which assumed that both position and momentum could be measured exactly. The uncertainty principle suggested that at the microscopic scale, nature itself is inherently uncertain and probabilistic. This idea of intrinsic uncertainty, which was a direct consequence of Planck's quantization hypothesis, had profound implications for our understanding of the nature of reality. The development of quantum mechanics was further solidified by the work of Paul Dirac, who sought to combine quantum mechanics with the theory of relativity. In the 1920 seconds and 1930 seconds, Dirac developed the relativistic quantum theory of particles, which included the prediction of antimatter particles that have the same mass as regular matter particles but opposite charge. The discovery of the positron, the antimatter counterpart of the electron, in 1932 was one of the key experimental confirmations of Dirac's theory, and it marked another milestone in the development of quantum theory. By the late 1920 seconds, quantum mechanics had become a fully developed theory that could describe the behavior of particles at the atomic and subatomic level. Quantum mechanics had not only solved the problems that classical physics could not explain, but it had also introduced new ideas that fundamentally changed our understanding of the universe. The concept of quantized energy, introduced by Planck, had blossomed into a comprehensive framework for understanding the behavior of matter and radiation. In this new framework, the universe was no longer a deterministic machine governed by classical laws. It was a probabilistic and uncertain realm where particles existed in multiple states and outcomes were governed by probability. The implications of Planck's hypothesis extended beyond theoretical physics into practical applications. The development of quantum mechanics led to the invention of technologies that have revolutionized our world, such as semiconductors, lasers, and quantum computers. The principles of quantum mechanics are at the heart of modern electronics, with semiconductors providing the foundation for computers, smartphones, and nearly every piece of modern technology. Lasers, which rely on the principles of quantum mechanics, have applications in everything from telecommunications to medicine. Quantum mechanics also gave rise to new fields of research, including quantum computing, which promises to revolutionize fields such as cryptography, artificial intelligence, and material science. Quantum computers, which harness the power of quantum states to perform calculations at unprecedented speeds, are already being developed by companies and research institutions around the world. These computers have the potential to solve problems that are currently intractable for classical computers, such as simulating complex molecular interactions and optimizing large systems. Planck's hypothesis was not just a breakthrough in physics, it was the beginning of a technological revolution. From the development of transistors to the discovery of quantum computing, Planck's quantization of energy laid the foundation for some of the most transformative technologies of the 20th and 21st centuries. The philosophical implications of Planck's work were also profound. The quantization of energy challenged our classical intuitions about the nature of the universe. In classical physics, energy was continuous, and objects followed predictable, deterministic paths. In the quantum world, however, energy was discrete, and the behavior of particles was governed by probability rather than certainty. This led to a new understanding of the nature of reality itself, and to questions about the role of the observer in the physical world. Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that the universe may branch into multiple realities depending on the outcomes of quantum measurements, challenging our classical understanding of determinism and causality. Max Planck's hypothesis that energy is quantized was the spark that ignited the quantum revolution. His idea, initially proposed to solve a specific problem in blackbody radiation, became the foundation of a new theory that transformed our understanding of the universe. From the smallest particles to the largest galaxies, quantum mechanics has provided the tools to explore and understand the physical world in ways that were previously unimaginable. And it all began with Planck's bold idea that energy is not continuous but discrete. The introduction of the Planck constant and the shift toward understanding the discrete nature of energy marked the beginning of the quantum revolution. Prior to Max Planck's work, energy had been considered a continuous quantity, one that could be divided infinitely. However, Planck's quantum hypothesis shattered this notion, proposing instead that energy exists in small, indivisible packets, or quanta. This idea was both simple and radical, challenging the prevailing defied framework of classical physics. The concept was initially proposed to solve the blackbody radiation problem, which classical physics had failed to explain. However, its consequences were far-reaching, eventually leading to a complete overhaul of our understanding of the microscopic world. Planck's introduction of the quantum and the formulation of the equation E equals h nu, where E represents energy, h is Planck's constant, nu is the frequency of radiation, provided a precise way to calculate the energy of electromagnetic waves. This was a monumental shift in thinking. No longer could energy simply be thought of as a continuous flow. Instead, it had to be understood as quantized, with only specific energy levels allowed in any given system. While Planck initially viewed this discovery as a mathematical convenience, it was soon realized that this concept of quantized energy was the key to unlocking many of the mysteries of the atomic world. The next significant development came in 1905, with Einstein's work on the photoelectric effect, where he extended Planck's idea of quantized energy to light. Einstein proposed that light was made up of particles called photons, each carrying a discrete amount of energy, proportional to the light's frequency. This revolutionary idea not only confirmed Planck's hypothesis, but also shifted the understanding of light from a purely wave-based phenomenon to one that could exhibit both particle and wave-like properties. This duality of light would become one of the foundational principles of quantum mechanics, later extended to matter itself. Following Einstein's work, Niels Bohr used Planck's ideas to explain the behavior of electrons in atoms. In 1913, Bohr introduced a model in which electrons orbit the nucleus in discrete, quantized orbits. These orbits correspond to specific energy levels, and when electrons jump between these levels, they absorb or emit energy in the form of photons. Bohr's model successfully explained the spectral lines observed in hydrogen, providing experimental confirmation of Planck's theory and further establishing the importance of energy quantization in understanding atomic structure. As quantum mechanics continued to evolve, the uncertainty principle, proposed by Werner Heisenberg in 1927, introduced a new paradigm. Heisenberg's uncertainty principle stated that it is impossible to precisely measure both the position and momentum of a particle at the same time. This principle arose directly from the wave-particle duality of quantum objects, and it signaled a departure from classical determinism. Whereas classical physics assumed that the behavior of objects could be known with absolute certainty, quantum mechanics embraced inherent uncertainty, revealing a universe governed by probabilities rather than certainties. These developments, originating from Planck's quantum hypothesis, culminated in the creation of a new theoretical framework that could describe the behavior of particles on the atomic and subatomic levels. Schrödinger's wave equation, Heisenberg's matrix mechanics, and Dirac's relativistic quantum theory together formed the basis of quantum mechanics. The theory not only solved long-standing problems in atomic physics, but also led to the discovery of new phenomena, such as quantum tunneling and the prediction of antimatter. Quantum mechanics quickly became one of the most successful theories in physics, explaining phenomena from atomic spectra to superconductivity, and eventually forming the basis of technologies such as semiconductors, lasers, and quantum computers. In the century following Planck's introduction of the quantum, the theory has continued to evolve and shape our understanding of the universe. The quantum revolution didn't just solve the problem of black-body radiation, it transformed the very nature of physics, opening up new realms of inquiry and creating technologies that have reshaped the modern world. The development of quantum mechanics stands as one of the most important scientific achievements in history, driven by the simple yet profound insight that energy is quantized, not continuous. The introduction of Planck's quantum theory marked a monumental shift in our understanding of the natural world. Prior to this, energy had been considered a continuous quantity, easily divisible into smaller and smaller units. This assumption was deeply embedded in classical physics, which worked well in explaining many macroscopic phenomena. However, the problem of black-body radiation, where classical predictions failed, highlighted that there were limits to this understanding. Planck's insight that energy is quantized, existing in discrete packets, or quanta, directly challenged this classical view and opened up new possibilities for understanding atomic and subatomic processes. The immediate impact of Planck's work was evident in the resolution of the black-body radiation problem. Classical physics, particularly the Rayleigh-Jeans law, predicted that the intensity of radiation emitted by a heated object would increase infinitely at short wavelengths. This was clearly unphysical and did not match experimental results. Planck's solution, proposing that energy could only be emitted or absorbed in discrete amounts, allowed him to derive a formula, Planck's law, that accurately described the observed radiation spectrum. This law became one of the foundational equations of modern physics and marked the beginning of the quantum era. The quantization of energy was further confirmed by Albert Einstein's 1905 work on the photoelectric effect. Einstein proposed that light, previously thought to be a continuous wave, was actually composed of discrete particles called photons. The energy of these photons was proportional to the frequency of the light, in line with Planck's formula. This provided compelling evidence for the idea that energy is quantized, and it was a key development in the creation of quantum theory. Einstein's work bridged the gap between light as a wave and a particle, setting the stage for the wave-particle duality that would later become central to quantum mechanics. As quantum theory developed, it became clear that Planck's idea of quantized energy had far-reaching implications. In 1913, Niels Bohr used Planck's concept of discrete energy levels to explain the structure of the atom. Bohr's model proposed that electrons could only occupy certain orbits around the nucleus, with energy being emitted or absorbed when an electron jumped from one orbit to another. This concept of quantized orbits successfully explained the spectral lines of hydrogen and resolved a number of outstanding issues in atomic physics. Bohr's work was a direct extension of Planck's ideas and established the importance of energy quantization in understanding atomic behavior. The development of quantum mechanics in the 1920 seconds, particularly the formulation of Schrödinger's wave equation and Heisenberg's uncertainty principle, further solidified the importance of quantization. Schrödinger's wave mechanics introduced the idea that particles like electrons could be described as waves, and the probability of their position could be determined from a wave function. This shift from a deterministic worldview to a probabilistic one challenged the principles of classical physics, which relied on precise measurements and predictable outcomes. Heisenberg's uncertainty principle, which stated that the position and momentum of a particle could not both be known precisely at the same time, added to this sense of fundamental indeterminacy. Quantum mechanics soon became the dominant framework for understanding the microscopic world. It provided answers to problems that had stumped classical physics, including the behavior of atoms, the nature of light, and the interactions between matter and energy. The theory's ability to explain phenomena like the behavior of semiconductors, the properties of superfluids, and the functioning of lasers led to numerous technological advancements. The invention of the transistor, which is the basis for modern electronics, and the development of quantum computers, which exploit quantum phenomena for computational power, are just two examples of how quantum theory has reshaped the world. The philosophical implications of quantum mechanics were profound. The concept that energy, light, and even matter could exist in quantized states led to a rethinking of the very nature of reality. The probabilistic nature of quantum mechanics, where particles do not have definite properties until measured, introduced a level of uncertainty that was previously unimaginable in classical physics. This uncertainty not only applied to the behavior of subatomic particles, but also called into question the role of the observer in determining reality itself. The famous thought experiment, Schrödinger's cat, was created to illustrate the paradoxes of quantum mechanics, where a particle could exist in multiple states simultaneously until observed. Such challenges to classical ideas of determinism and causality were not just scientific revelations, but also deeply philosophical inquiries into the nature of knowledge and existence. In summary, the impact of Planck's quantization of energy cannot be overstated. His hypothesis laid the foundation for the quantum revolution, fundamentally altering how we understand the universe. Planck's idea that energy is quantized transformed not only theoretical physics, but also led to the development of technologies that have revolutionized industries and changed the way we live. From the development of atomic theory and quantum mechanics to the advent of modern technologies like computers and lasers, the consequences of Planck's work have shaped the modern world in ways that continue to unfold. Quantum mechanics remains the most successful theory of the microscopic world, and it all began with Planck's insight that energy is not continuous, but discrete. Max Planck's hypothesis, which introduced the idea that energy is quantized, represented one of the most pivotal moments in the history of science. The concept of quantized energy radically departed from the classical view, where energy was thought to be a continuous flow. Planck's insight began as an attempt to resolve the blackbody radiation problem, where classical theories had failed to account for the observed spectral behavior of heated objects. Prior to Planck's work, it was widely believed that energy could be emitted or absorbed in any amount, a view that proved to be inaccurate when confronted with experimental data. Planck proposed that energy exists in discrete units, or quanta, which could only take on specific values. This fundamental shift in understanding not only solved a key problem in physics, but also laid the groundwork for the development of quantum mechanics. The immediate consequence of Planck's hypothesis was the resolution of the ultraviolet catastrophe. Classical physics, particularly the Rayleigh-Jeans law, predicted that the intensity of radiation emitted by a heated object would increase without bound at shorter wavelengths. This prediction was absurd, as no physical system could emit infinite energy. Planck's formula, which connected energy to frequency with the equation E equals h nu, where E is energy, h is Planck's constant, and nu is frequency, allowed him to derive a new equation that accurately described the intensity of radiation. This marked the beginning of the quantum revolution and signaled a break from classical physics, introducing the concept that energy was not continuous but instead existed in discrete packets. The next breakthrough came in 1905 when Albert Einstein extended Planck's idea to light itself. Einstein's work on the photoelectric effect provided clear evidence that light, which had previously been treated purely as a wave, could also exhibit particle-like behavior. In the photoelectric effect, light striking a metal surface causes the emission of electrons. Classical wave theory could not explain why only light of certain frequencies, regardless of its intensity, caused this emission. Einstein proposed that light was composed of particles, or photons, each carrying a discrete amount of energy, proportional to the frequency of the light. This idea not only confirmed Planck's concept of quantization, but also set the stage for the broader understanding of wave-particle duality. Following Einstein's work, Niels Bohr applied Planck's quantum theory to the structure of the atom. In 1913, Bohr introduced his model, which proposed that electrons orbit the nucleus at discrete energy levels. These levels, like the quanta of energy in Planck's theory, were not continuous but quantized. Bohr's model successfully explained the spectral lines of hydrogen, which had long puzzled scientists. When electrons transition between energy levels, they absorb or emit energy in the form of light, with the frequency of the light corresponding to the difference in energy between the levels. Bohr's model was an important step in the development of atomic theory, directly incorporating Planck's idea of quantized energy into a new understanding of atomic structure. The next stage in the quantum revolution was the development of quantum mechanics in the 1920 seconds. This included the wave mechanics of Erwin Schrödinger and the matrix mechanics of Werner Heisenberg. Schrödinger's wave equation treated particles like electrons as waves rather than as discrete points, and showed that the properties of particles could be described probabilistically. This was in direct contrast to the deterministic approach of classical mechanics, where every aspect of a system could be precisely determined. Schrödinger's equation provided a mathematical description of how quantum particles behave, revealing that particles can exist in a superposition of multiple states until measured. This probabilistic nature of quantum mechanics was a significant departure from the classical worldview and echoed Planck's introduction of quantized energy, which laid the groundwork for this uncertainty. The uncertainty principle, introduced by Heisenberg in 1927, was another crucial result of quantum theory. It stated that it is impossible to simultaneously measure both the position and momentum of a particle with absolute precision. The more accurately one of these quantities is measured, the less precisely the other can be known. This principle was a direct consequence of the wave-particle duality of quantum objects and had profound implications for the way we understand the physical world. In classical physics, the idea that objects could be precisely measured was a fundamental assumption, but quantum mechanics showed that there are inherent limitations to knowledge at the microscopic scale. Together, the ideas of Planck, Einstein, Bohr, Schrödinger, and Heisenberg transformed our understanding of the atomic and subatomic world. Planck's quantum hypothesis, which began as a solution to a single problem in blackbody radiation, became the foundation for the development of quantum mechanics. This new framework explained phenomena that classical physics could not, such as the discrete nature of atomic spectra and the wave-like behavior of particles. Quantum mechanics also provided the basis for a range of technological advancements, from the development of semiconductors and lasers to the emerging field of quantum computing. The quantum revolution had a profound impact on both science and technology, shaping the modern world in ways that continue to unfold. The consequences of Planck's discovery extend beyond just solving specific problems in physics. His work marked the end of an era in which classical physics reigned supreme and ushered in a new age of exploration at the atomic and subatomic levels. The world of quantum mechanics is strange, counterintuitive, and fundamentally different from the world of classical physics, where objects follow predictable paths. In quantum mechanics, uncertainty and probability rule the day. These ideas have not only shaped our understanding of the microscopic world, but have also challenged our very conception of reality. Quantum theory has opened up new frontiers in science and technology, giving us tools to explore and manipulate the natural world in ways that were once unimaginable. As we continue to probe deeper into the quantum realm, we will likely uncover even more surprises, all stemming from the simple but profound insight that energy, matter, and light are not continuous, but quantized. This idea remains at the heart of modern physics and will likely continue to shape our understanding of the universe for generations to come. Max Planck's hypothesis that energy is quantized stands as one of the most transformative ideas in the history of physics. Prior to this, energy was understood as a continuous quantity, an assumption that governed classical physics. The belief that energy could be divided indefinitely into smaller parts worked for most macroscopic phenomena. However, when it came to understanding the behavior of radiation emitted by hot bodies, classical physics failed. The problem became clear with the study of black-body radiation. Classical theories predicted that as the wavelength of radiation became shorter, the intensity would increase infinitely, a prediction known as the ultraviolet catastrophe. This paradox revealed that the classical understanding of energy was inadequate, and the need for a new framework was pressing. Planck's insight provided the answer. In 1900, while studying the problem of black-body radiation, Planck proposed that energy is not continuous, but instead exists in discrete packets, which he called quanta. This was a radical departure from the classical view and laid the groundwork for the development of quantum theory. Planck introduced the idea that the energy of these quanta is proportional to the frequency of radiation, with the relationship given by E equals h, nu, where E is the energy of the quantum, He is Planck's constant, and nu is the frequency of radiation. This simple equation would revolutionize the way scientists thought about energy and radiation. While Planck's work solved the problem of black-body radiation, he himself did not fully grasp the deeper implications of his discovery. His hypothesis was initially seen as a mathematical tool designed to fit the experimental data, rather than a fundamental shift in understanding. However, the breakthrough was profound. Planck's theory provided a way to reconcile the discrepancies between theory and experiment, which had eluded classical physics for years. This work set the stage for the quantum revolution, where the idea of quantized energy would have far-reaching consequences, not only for radiation, but for the behavior of matter itself. Albert Einstein's extension of Planck's idea to light in his explanation of the photoelectric effect in 1905 provided further evidence for the quantization of energy. Einstein proposed that light, previously thought to be a continuous wave, was made up of discrete particles, which he called photons. The energy of each photon, he argued, was proportional to the frequency of the light, just as Planck had suggested for radiation. This provided crucial experimental support for the notion of quantized energy and showed that light itself could exhibit both particle-like and wave-like properties, laying the foundation for the development of the wave-particle duality. Niels Bohr took Planck's ideas further in 1913 when he introduced a model of the atom in which electrons orbited the nucleus in discrete energy levels. According to Bohr's model, these energy levels were quantized, and the emission or absorption of energy by electrons occurred when they transitioned between these levels. This was a direct application of Planck's hypothesis to atomic structure, and it provided an explanation for the observed spectral lines of hydrogen. Bohr's work reinforced the idea that energy was not continuous, but instead existed in specific, quantized states. As quantum theory continued to develop, it became clear that the implications of Planck's hypothesis went far beyond blackbody radiation. The probabilistic nature of quantum mechanics, encapsulated in the uncertainty principle introduced by Werner Heisenberg in 1927, suggested that the act of measurement itself could never reveal an object's exact position and momentum simultaneously. This was a direct result of the quantized nature of energy, and it marked a fundamental departure from classical physics, which assumed that all properties could be measured with absolute precision. The wave-like behavior of particles, described by Erwin Schrödinger in 1926 with his wave equation, further built on the idea of energy quantization. Schrödinger's equation demonstrated that particles like electrons could be described as waves, existing in a superposition of states until measured. This concept introduced a new way of thinking about particles, emphasizing probability and uncertainty rather than deterministic paths. The equation also helped establish that the quantization of energy was not just a theoretical construct, but had practical, observable consequences for the behavior of subatomic particles. In the decades following Planck's introduction of the quantum, the implications of his discovery became increasingly evident. The development of quantum mechanics provided answers to questions that had stumped classical physics, including the nature of light, the behavior of electrons, and the structure of atoms. Quantum theory became the foundation for many of the technologies that define the modern world, including semiconductors, lasers, and quantum computers. These technologies, which rely on the principles of quantum mechanics, have revolutionized industries ranging from electronics to medicine. In conclusion, Planck's hypothesis that energy is quantized was the catalyst for a scientific revolution. It transformed the way scientists understood the nature of energy, light, and matter. What began as a solution to a specific problem in blackbody radiation became the cornerstone of quantum theory, which continues to shape our understanding of the microscopic world. The development of quantum mechanics, driven by Planck's insight, not only provided answers to long-standing questions, but also led to technological advancements that have reshaped the modern world. The quantum revolution, which began with a simple idea about the nature of energy, has proven to be one of the most important intellectual breakthroughs of the 20th century.